Okay, so let's talk about decimal representations. It's easy to take this kind of representation of numbers for granted, but there's a lot of information, and it took many centuries to develop a system like this that contains so much information in such a compressed form. All right, so one example is the number 72483. We know that the place of the digit determines the power of 10 that it multiplies. So we can technically write 72483 because the 7 is in the fifth place over, so it multiplies 10 to the fourth. 2 is the fourth place over from the right? That's first place, second place, third place, fourth place. So this is a ones place, tens place, hundreds place, thousands place, 10,000s place. Okay, so I've broken out these digits in this way, and you can see how this works. Now, if you're thinking about mod 10, this gives you a very nice way of seeing how this number relates to mod 10, right? If I take mod 10, then 7 times 10 to the fourth, that's 0 mod 10, 0 mod 10, 0 mod 10, 0 mod 10. I just get 3. Right. Now, if I wanted to do mod 100, I'd have a similar sort of decomposition. 10 to the fourth is a multiple of 100. 10 to the third is a multiple of 100. 400 is a multiple of 100, so I just have the 83 left over. Okay. So we're going to use this notation of of the mth digit as dm. Okay, the digit in the ones place I'm going to call d0. Now, why do I call it d0? Because 1 is 10 to the 0. d1 corresponds to 10 to the 1. d2 corresponds to 10 to the 2. So, and note that each digit dj must be in z10. So this relates to the previous chapter. So we'll be talking about integers mod 10 when we talk about coefficients of decimal digits, of decimal numbers. All right, so let's go down to the next part. All right, now it's easy for us to read off the digits of a decimal number. But for a computer, it's not so easy because, in fact, computers don't store numbers in decimal. They have some other representation. If you know, it's called a binary representation. But what we want to do is to develop a formula, a mathematical formula that allows me to get the digit from this decimal number. Again, you might think this is a waste of time because if I want to, say, find the 100th digit, I can see from the number that it's 4. But I want a formula that a computer could use to find the digit of this number. All right, so in this section, we're going to describe a process by which we can get all the digits one by one, starting from right to left. Okay, and this is a procedure that you could code into a computer and use the computer to find the digits one by one of your decimal number. Okay, now we remarked before that when we have a number like this, if I'm going to take this number mod 10, the result is simply going to be the ones digit because all the other digits multiply powers of 10. Okay, so we have this, in this case we have 3 is the mod of this number in base 10. Okay, it's the remainder mod 10. 3 is the remainder mod 10. Okay, now if I subtract 3 from n, I get 72480, which is divisible by 10. If I divide by 10, I get 7248. Now if I want the 8, I can do the same process again, right? If I take the remainder of this mod 10, or mod of 7248 comma 10, I'm going to get 8. Okay, then if I subtract 8, as I do down here, I get a number divisible again by 10, and I can divide by 10, get 724. Then I can take the remainder of that mod 10 and get 4, so on, so on, so on. So you can see we have a process that we can go run again and again and again. This is called an iterative process. Okay, so the first step in the process was to take my my 0 place digit, which was the remainder of n mod 10. Then I subtracted that, so that was my first digit. Then I subtracted that digit from n and divided by 10. And then I did the same process. I took the remainder of that result mod 10, subtracted it from the number, divided by 10, and so on. So you can see that we've expressed that in this series of commands down here. My starting value is n, the number I start with. D0 is the remainder of that number mod 10. Then from that I form a new number, A1, which is A with the A0 minus the D0, divide by 10. And then D1 will be the remainder of that result, mod 10. And I just keep going and going and going and going like this, okay? Now we can summarize this sequence this way. Each step in the sequence depends on the previous sequence in this way, in the previous step in this way. All right, AK, for instance, if K equals 2, I would have A2. If K equals 2, then K minus 1 is 1. So I get A2 equals A1 minus D1 over 10. So that's exactly what I have here. Okay. So this gives the general step and I just repeat this step as long as I need to, all the way up to the last digit in the number. Okay. So we can call this recursive or iterative because you're repeating the same calculation again and again. All right. So you can apply this. You could try doing this on the computer. That would be kind of interesting. You could do it on the computer. Okay. All right. So let's see. Now, suppose we don't want to find all the digits. We want to just go directly and find a particular digit in a long number. And we don't want to do a long recursive process. Okay, so let's find the digit D6. Now remember, D6 is in the 10 to the 6th place. So this is D0, D1, D2, D3, D4, D5, D6. D6 is the one that multiplies 10 to the 6th. Okay, so it's actually the 7th place in the number. Okay, now what we can do is we want to remove the digits above and the digits below. Okay, we can remove the digits above because all of these numbers up here multiply powers of 10 that are 10 to the 7th and above, right? 8 multiplies 10 to the 6th. 2 multiplies 10 to the 7th. 9 multiplies 10 to the 8th. 1 multiplies 10 to the 9th. All these digits represent numbers that are divisible by 10 to the 7th. So if I take mod 10 to the 7th, those will go away. Okay, so if I take this number and take the remainder mod 10 to the 7th, I just get this. Now I want the top digit. How can I get the top digit? Well, I could remove this 8th digit by taking the bottom 6 digits, bottom 7 digits this way, bottom 6 digits, sorry, bottom 6 digits, and then I can subtract this number from this number and I get my 8. Okay, so you see how I can make that work. Okay. So I took the remainder mod 10 to the 7th and I subtracted the remainder mod 10 to the 6th and I got 8 times 10 to the 6th. So I just divide by 10 to the 6th. So here's my formula for D6. Okay, that's how I can get the digit that corresponds to 10 to the 6th. Now you can kind of see how this works. You can see there's a 6 here and a 7 there and a 6 here and a 6 there. If I replace this 6 with, say, 12, right, then if there was a 12 here, it makes sense that this would be a 13. This would be a 12, this would be a 12. All right, so we can think that no matter what number k I put in here, this number is going to be k plus 1, this is k, this is k. So here's my general form for finding the kth digit of a positive integer. All right, and here's some exercises to give you a chance to do that. Okay, I'm going to stop here for a moment just to keep these videos short, and we will pick up with another video to do the next section.